Hello, hello. Can you hear me? Does that work? It doesn't work. It works? Okay, it works. Ah. So I have to speak loudly. So first of all, well, good morning. Thank you for being so many. It's really great to see so many people in this amphitheater for this occasion. So this is today the first general seminar of IPhT of the season. I hope that there will be other ones and that they will be as successful as this one. Today, so we have the great pleasure to receive il professore Gabriele Veneziano. So I will do a little introduction about Gabriele. So Gabriele received his PhD at the Weizmann Institute in Israel in 1967. Afterwards, he went to a very small American institution known as the MIT. He then returned at the beginning of the 70s to the Weizmann, I think as a professor, if I understood correctly. Afterwards, from 1976, he took a permanent position at CERN, another very small and unknown, obscure institution, but this time in Europe. He's actually been the director of the theory division of CERN so from 1994 to 1997. Is that correct? Gabriele, you correct me? Yes, all good so far. So Gabriele received a number of prizes and medals and things that, well, I think the only one that's missing is the Nobel Prize, so I'll not do the whole list of it. But there is one I really liked. In 2007, you've been ordered Commendatore al Merito della Repubblica Italiana, which I think sounds amazing. I think this should be our objective in life to get these kind of titles. Commendatore Veneziano from now on. Yes, but I think actually the best achievement of Gabriele is that he has been obtained the position of professeur honoraire du Collège de France, which I think beats everything, right? So Gabriele is mostly known for being, as people say, the father of string theory. So the discovery initially motivated by explaining the strong interaction that then led to string theory. So many of you wouldn't be here if Gabriele weren't here today. But then at some point, I think Gabriele returned to reason by working a little bit on cosmology. I mean, in 1991, motivation of inflation via string-motivated scenario, and also a little bit of classical GR and cosmology towards the years 2010, I think, on the propagation of light in homogeneous universes, which definitely is much more interesting than string theory. But today, Gabriele is going to talk about scattering amplitudes, and I'm very happy to give you the floor right now.
Ça va? No? Oui? Oui? All right. So this is going to be some kind of very general overview of a problem on which I have worked for now some 35 years. So of course the subject is very broad. I will try to, as I say, to have a non-technical overview of the subject, and I apologize in advance to the many experts in the field which are around here. So let me start with an introduction. As you know, there have been this spectacular direct detection of gravitational waves a few years back. And this has boosted, of course, a very rich and ambitious experimental program, exploiting existing interferometers or planning for new ones. Now, in parallel, this discovery has boosted theoretical work on the two-body problem in general relativity, and mainly this is done by some traditional methods for computing the expected waveforms and therefore interpret the signals. Those are, I remind you, are for instance numerical relativity, the post-Newtonian expansion, and the effective one-body approach. These are all essentially classical approaches. They don't take quantum mechanics into account, but new avenues have been followed based on taking the classical limit of quantum mechanical scattering amplitudes. These have also been vigorously pursued, and this fact brought together two theory communities. One is the already mentioned from classical general relativity, and the second one is from high energy particle physics, okay, for whom the amplitudes, as it was mentioned, are the bread and butter research. Now, this has generated a lot of synergy between the two communities. For example, there have been several workshops, the so-called amplitudes series of conferences, the QCD meets gravity series of conferences, and so on. And however, the high energy community has been actually interested in the gravitational two-body problem since many years, since the late 80s. There have been pioneering work by Herr Toft, by our group, Muzinich and Soldate, and many, many others have contributed. But the motivations at the time were completely different from those that prevail today. Now, in that case, one was interested in the two-body problem, but the two bodies were elementary particles, therefore light objects compared to the Planck mass. And in that context, taking trasplanckian energies larger than the Planck mass, are crucial in order to make gravity relevant. We know that in accelerator physics, gravity is usually negligible. If you want to make it relevant at all, if not dominant, you have to go necessarily to super Planckian energies. I remind you that gravity couples to energy. So the ultra-relativistic limit was very essential in those days. Now, besides, ultra-high energy are also needed to justify taking a classical or semi-classical approximation, as we will see in a moment. However, what was completely missed at the time, at least by myself, was that at large enough distance, massive black holes can also be thought of as elementary particles. This is somewhat related to the no-hair theorem, saying that the black hole, the outside region of a black hole is just determined simply by its mass and its spin, like it's the case for an elementary particle. And then, if that is so, then those Gedanken experiments of those old days become all but Gedanken. They become very relevant. Now, of course, for black holes, for physical black holes, astrophysical black holes, which are much heavier than the Planck mass, it is not the ultra-relativistic regime which is most relevant. It's the opposite. It's the non-relativistic regime which is most relevant. Some occasionally, precisely near the coalescence of the two black holes, maybe you get into some mildly relativistic regime. So However, since the non-relativistic regime seems to be the most relevant one, and the old work was based on the ultra-relativistic approximation, you could say, well, should we forget about that old earlier work on the subject? Is it going to be completely irrelevant for the black hole problem? So I will try to convince you that the answer is actually no, that you shouldn't forget about that earlier work. And actually, Thibaut Damour in 2017 has already argued that useful input to the effective one-body approach can be obtained from the high energy, therefore ultra-relativistic regime of gravitational scattering, and gave an example which I will mention in a moment. Now, there are other examples of useful connections between the ultra-relativistic limit and the classical two-body problem in GR, and this will be one of the main topics of this talk. So this is an outline which, well, if you want, is a sketch of these 35 years of work on the subject. As I said, I will not be able to cover everything and anything in any depth, but just to give you a little framework, let me mention various activities in the field. So in the first, say, 20 years or so, the attention was on particles and string. So light particles or light strings interacting gravitationally at a very high energy, where we could identify essentially three main regimes for the problem. One which we can call weak gravity, second string gravity, and third strong gravity. So I will very briefly review the main results in those days. Then we had a first attempt at computing gravitational radiation from these collisions, but we met an energy crisis which later on was almost solved. It's a kind of puzzle that we called an energy crisis, to give it a fancy name. And later on, this was almost completely solved, but we will see that it is not yet fully solved. Then there have been also work dealing with string scattering on stacks of D branes. This, for instance, in my case, took place in the years 2010 to 15. I will have no time to talk about that subject, only to tell you that this is somewhat related in the present setting of black hole collisions to the so-called probe limit, okay? Because the stack of D branes is much heavier than the strings that collide on it. So it's a little bit similar to the problem of, to the test particle limit in the scattering of black holes. And then since 2019, my activity has been concentrating now on black hole collisions up to third post-Minkowskian order, as I will explain, where, we went through several interesting topics, and there is also a second energy crisis that I will describe. And finally, these days, I'm mostly working on trying to construct a unitary semi-classical S-matrix to describe these processes. Now, so let me start with the subject of light particles or strings. As I said, the motivations at the time were purely theoretical. On one hand, we wanted to recover perturbative unitarity, to see from this purely quantum mechanical calculation in flat space-time, the emergence of classical and quantum gravity effects. I underline this was done by computing scattering amplitudes in flat space-time, and yet you can see an effective metric, curve metric coming out of the calculation. And the other thing was to check unitarity. The other aim was to check unitarity even in regimes where the process is expected on classical grounds to lead to black hole formation. If you could check unitarity even in that regime, then you would have an answer to the famous information puzzle in black hole physics. As you will see, this has not been as successful so far. The first part, I think, was quite successful. So let me remind you of what is the parameter space for the various regimes that one wants to describe. If you have a collision of two, say, light and spinless even particles, then the parameters in the problem are the angular momentum of the process, but if you prefer, the impact parameter, which is related to angular momentum by the well-known relation. Then you can associate with the center of mass energy a length scale, according to GR, which we can call the Schwarzschild radius associated with the center of mass energy. Then if you are in string theory, there is a string length parameter. And then since you are also in quantum gravity, in principle, you also have a Planck length. Now, you can get rid of the last length scale, the Planck length, if you work at very small string coupling, because then the Planck length is parametrically smaller than the string length, and the only relevant scales remain the first three. You can form two-dimensionless ratios, and therefore the phase diagram becomes two-dimensional, and the following different regimes emerge. So if you have on the vertical axis the impact parameter, and on the horizontal axis the gravitational radius r, and now you mark, say, as a reference scale the string length, then you see you divide this plane in three regions. Region 1, you have weak gravity. At large distance, gravity becomes weak. You know, it's just the opposite of a gauge theory, like UCD. Then, in region 2, you see the string length dominates over the other scales. So this is where you emphasize, as much as possible, string size effects, which is a very interesting region. And then, in region 3, the gravitational radius dominates over the other two scales, and that's where you expect to find gravitational collapse. And the classical arguments based on constructing closed trap surfaces during the process suggest that red line as the boundary between the collapse region and what is called the dispersion region, in which all the incoming energy is eventually radiated out at infinity. You can interrupt me if you want. It will just take a little bit longer to finish, or I will have. But I mean, if you find that it's unclear, please feel free to interrupt. So in the region 1 of weak gravity, as I already mentioned, we could see gravitational deflection emerge, the time delay, Shapiro time delay emerge, tidal excitations of of the string, if you are doing string-string collisions. And as I said, also a first calculation of gravitational Bremsstrahlung in this regime. In this regime, the typically the two particles or the two strings deflect each other's trajectory by a small angle, which is of the order of the ratio between R and B, as we will see. You see that you restore elastic unitarity via a resummation of S-channel ladders. In perturbation theory, if you go to very high energy, you seem to lose unitarity, the boundedness of partial wave imposed by unitarity, but after this eikonal resummation, elastic unitarity is nicely recovered, and gravitational deflection and time delay emerge as you would expect from the production of a shock wave metric. Okay. This also goes back to ideas of Toft. And this was extended in 1990 up to order G cubed. G is the Newton constant. An interesting point, which is often emphasized, is that there is some kind of fractionation of momentum, transverse momentum, which is exchanged between the two colliding particles. So you can get a hard scattering, in the sense large momentum transfer process from large distance physics. This sounds very unfamiliar if you are thinking in terms of particle physics, say QCD, but in gravity this happens, and if you want, the big momentum transfers gets shared among a huge number of gravitons which are being exchanged, each one of which carries a very small momentum. And that's why the process itself is large distance. I mean, this is the formula which illustrates how the total momentum transfer is of order h bar over b, which is a very small quantity, but times a large number, gs over h bar, which is the number of gravitons that you are exchanging. So you get a big kick out of many, many small kicks. Now, the deflection angle, as I said, is computed from an eikonal phase, which itself, parameterizes the S matrix in B space, impact parameter space, and scattering angle and time delays are obtained as derivatives of this phase delta, either with respect to impact parameter or to energy. On the other hand, if im delta is different from 0, in fact is positive, then the elastic S matrix is damped, is reduced, and this is related to the opening of inelastic channels and to the consequent suppression of the elastic one. I'll give some examples below. Okay? So as long as delta is real, the absolute square of S is 1, and the process is purely elastic. But when inelastic processes occur, it is well known from particle physics that the elastic amplitude gets diluted. Okay, so this is a little summary of the results in our work of 1990 up to 3 p.m. Third post-Minkowskian order means up to 2 loops. okay? So 1 p.m. means 3 level, 2 p.m. means 1 loop, 3 p.m. means 2 loop. So at 3 level, 3 in an effective sense, there is this infinite resummation of ladders, but if you want the exponent, this exponentiates, and what you have to expand is the exponent, okay? That's very important. So when you do this at 1 p.m., you get this phase shift of this eikonal phase, and this gives the typical Einstein deflection when you differentiate with respect to B, or the Shapiro time delay if you differentiate with respect to the energy. Now, at 2 p.m., and this is a classical result, you see the fact that the phase goes like 1 over h bar is just a signature that this is a classical, think about WKB approximation. Now, instead, if you go to 1 loop, I'm talking about the massless case, massless situation, ultra-relativistic situation, surprise, you find that the delta 1, the first correction, does not have the 1 over h bar. So that is a quantum correction already. It turns out to be non-universal. And this is the use of the ultra-relativistic limit that I mentioned earlier by Damour. He made use of the fact that at 2 p.m. The result should go to 0. The classical result should go to 0. Instead, if you go to 3 p.m., 2 loops, the result is again classical. The correction, if you want delta 2 to the eikonal phase, is again classical because you see it has this nice 1 over h bar there. It is finite. That's what we found. No divergence. And if you differentiate this with respect to B, you get 1 over B cubed. Then you have to also divide by square root of S, and you find a correction to the deflection angle, which is perfectly finite. Now, instead, if you look at, for the first time at this level, you find that there is an imaginary part as well, an absorption, and that is classical again, but is also divergent, logarithmically divergent. And we will see, this is the famous infrared divergence that you would expect anyway, and we'll see what to do with it. Okay, so this is the result for particle-particle scattering. If you go from particle-particle scattering to string-string scattering, then you find that there is another reason for inelastic processes, which is due to the to tidal excitations of your strings. Your strings being extended objects, you expect, okay, that in a non-trivial metric they suffer from tidal forces. And in fact, what you see quantum mechanically is that if you start, say, with 2 massless strings, after the collision, they can form 2 massive strings, or 1 massive and 1 massless. And this is the quantum analog of the tidal excitation, the classical tidal excitation. And what we found already in '87 is that, from calculations, this is not a guess, that you can describe the effect of the string size by replacing the eikonal phase. You see, my previous formula, you replace the eikonal phase delta by a delta hat, where delta hat is delta evaluated not at B, but at B plus some displacement, which are nothing but the string coordinate with respect to its center of mass of the 2 strings. xu and xt mean the up and down string in this picture, and the whole thing is then averaged over the sigma, the spatial coordinate of the string. This is a nice emission operator. So this defines a unitary operator which describes the excitation of the tidal excitation of our strings, but it's perfectly unitary. So instead of having elastic unitarity, you have full inelastic unitarity in this approximation. And you can describe, the spectrum of excitations. You can study the microstates which are excited. There is a lot of beautiful things you can try to do. So this worked very beautifully. Now, then we had a first go at Bremsstrahlung, but this produced what I mentioned already, an energy crisis, a puzzle, and this we will describe below. Okay, then if you go to the string gravity regime, well, there you find very interesting effects too. Fortunately, that regime is also accessible to some perturbative calculation, so it's under control. It's quite under control. You see that string theory softens quantum gravity as small impact parameters. This solves a potential causality problem pointed out in a nice paper by Edelstein, Maldacena, et al. And this was checked in particular in string-brain collision, but it also works in string-string collisions. Okay, then there are other interesting things which I will skip over, otherwise we will be too late. Just a few words about the bad beast in the game, which is the strong gravity regime. Of course, this would be the most exciting thing to do, because if you, as I said, if you could construct your unitary S matrix in that regime, you would solve the information paradox puzzle. So all we could do was to identify the semi-classical contributions in terms of some connected trees. I will skip the details. We could construct an effective two-dimensional field theory that resums these trees. Unfortunately, it becomes two-dimensional and simple after some truncation. Nonetheless, even this effective two-dimensional field theory is able to capture the existence of some critical critical parameters, or it's a multidimensional space, so some critical surfaces beyond which something bad happens to unitarity. So you'd like to identify those surfaces with a transition to the collapse regime. And in fact, the agreement is quite good with this collapse criteria. But unfortunately, as you go beyond those critical surfaces and you try to enter the collapse regime, there is a unitarity deficit which is not accounted for by some inelastic processes. And we got a bit stuck there. I switched to something else, but for instance, Ciafaloni and Colferai have written quite a number of interesting papers, but I think, to be honest, the problem of how to describe that regime is still not solved. As I said, there had been approximation made on the way, so perhaps it's a fault of some approximations. Okay, so at least I myself switched to simpler problems, which are still not so simple. One is gravitational radiation, that I will explain quickly. And the second is this program of studying string-brain collisions, where, for instance, an interesting thing is some new form of absorption. There you don't have black hole formation, but what happens is that your say, closed string, which moves in the bulk, can hit the stack of D brains, and you know, D brains, try to have open strings attached to them, and that's exactly what happens. If you go to small impact parameters, the closed string gets captured by the D brain system, which generates open string excitations on it. And one can study this closed open transition. Unfortunately, no time to talk about it, but there is a series of papers by those people. So, but let me turn to gravitational radiation, because this is very much more topical as a subject, and the first energy crisis. Now, what happened in the paper we wrote in 2007 with Amati and Ciafaloni is that we got a spectrum of radiation which was too hard. Namely, if you look at the spectrum, the energy emitted in gravitational radiation, differential spectrum in transverse momentum and frequency, we got a nice cutoff in transverse momentum, but a very mild one in frequency. Remember that we are working at small deflection angles, so that means that R square over B square is a very small number. That means that the cutoff in omega, in the frequency of the gravitational wave, is very weak. And as a result, we found that the total emitted gravitational energy became of the same order as the full incoming energy already for some small deflection angle. And that doesn't make sense. I think it was Richkov, the one who pointed out this problem. And now, as I was mentioning, this problem has been almost solved, and I want to describe briefly how it was solved by two different approaches. One is a purely classical approach that I carried out with Andrei Gruzinov at NYU, when I was visiting NYU some time ago. And a second one, a little bit later, is a completely quantum amplitude-based approach. And it's very nice to see that these two approaches, which apparently have nothing to do with each other, give exactly the same answer as you send h bar to 0. Now, however, let me mention something which then becomes relevant later on. How am I doing? So and so. So before embarking in those non-trivial calculations, I mean, we, Gruzinov and myself, we checked the literature on, what is the gravitational radiation. It looked like the simplest problem you can think about. Two massless particles collide, they deflect at large impact parameter, they deflect by a small angle. One should be able to compute how much gravitational radiation comes out of the process. So we checked the literature, found nothing, asked the experts, including numerical relativity people, and each time, the typical answer was, oh, that should be very simple, I'll give you an answer next week. And then, nothing came out. So the feedback was very disappointing. And so we decided to Gruzinov and myself, to look at it. Now, on the way, we found some old papers by Kovacs and Thorne, which was warning on the limit of validity of the of their 1977 results. So we decided, okay, and the warning of Kovacs and Thorne, this is the abstract of their paper where they say they do the ultimate definitive treatment of classical gravitational Bremsstrahlung, however, with a little bit of warning, a little warning that the angle of gravitational deflection should be much smaller. You see that 1 over gamma, okay, the Lorentz gamma factor. So in notations which I will use later, where gamma is called sigma, okay, that means that you have to take the scattering, the deflection angle, times the Lorentz boost factor much smaller than 1, which of course prevents you from going to fixed angle and sigma to infinity. So, in other words, already Kovacs and Thorne in 1977 put a warning, be careful. You can do lots of things, but stay away from the ultra-relativistic regime, okay? So, and this actually, I mean, I should give much credit, perhaps even more than to those two authors, to Peter Diaz, who really was the one who pointed out. Okay, I will refer loosely at that bound theta times sigma to the 1/2 less than 1 as the KT bound for Kovacs and Thorne, but I think Diaz should be added to it. So anyway, so we decided to do it ourselves from scratch. We got much inspiration from Diaz's work, who went really quite a long way towards the massless limit, but stopped short of doing it. And we discovered that the massless limit was not that hard, but okay, without going into the details on how we got it through some Huygens principle construction and so on, I'll just flash the final result. You see, it's not extremely simple, but it's not very complicated either, because we compute this C, which are the so-called News functions, which control the amount of gravitational radiation in the process, in terms of a two-dimensional integral. Okay, here we are in 4 dimensions, and these are the notation. You see, this is our R, which is more precisely defined. This is the deflection angle at leading order, and this is what we got. But one should emphasize that since R contains Newton's constant, and R appears in this exponential form, this is already a resummation of many post-Minkowskian orders. So this shows already that somehow this ultra-relativistic limit is not very comfortable with the post-Minkowskian expansion. So this is the explicit formula, which is, you can put it in Mathematica and do the computations. Of course, things oscillate quite a lot, so sometimes precision becomes tricky. So now we found some analytic results and some numerics, and in particular I want to emphasize that what we found is what we called a Hawking knee, and also an unexpected bump at some values of omega. So you look at the spectrum as a function of omega in units 1 over b. Here there is no h bar. Omega is a frequency, not an energy, and b, of course, is a length. I use c equal 1 everywhere, but I try to put the factors of h bar where they are needed. So this is how you can study analytically the spectrum, and then also numerically. And the spectrum is almost flat at small frequency if you are below 1 over r, but above 1 over b. And then if you try to go below 1 over b, so very, very small frequency, the spectrum becomes actually constant, and you get this constant limit, which is called the zero frequency limit, ZFL, goes back to work by Smar. You can derive it by using the soft theorems in gravitational physics, and this is the expected result. So okay, that complicated formula reproduces exactly the expected zero frequency limit of the spectrum. That is not so exciting. What is more exciting is that as you go above 1 over r, remember r is much smaller than b, so 1 over r is much bigger than 1 over b. So you are now in this regime, which is already away from where you can apply the soft theorem. So you are no longer dealing now with soft gravitons. They are slightly more energetic, although you see their energy is still of order h bar over r, okay? So still small, classically speaking. So the spectrum, from being almost constant, becomes 1 over, turns into a 1 over omega spectrum. We call it scaling variant, but I mean, it's just a name. And this you can see very much also in numerical calculations. So the spectrum is initially very, this is a spectrum at different values of theta. It goes to this ZFL, zero frequency limit, which changes logarithmically with theta. It's already normalized by a GS theta square. So what is left is almost constant, but it still depends a little bit on, I mean, it goes to a constant which itself is logarithmically dependent on theta. But the interesting thing is that you see when omega is of order 1 over r, so you are near 0 here, all of a sudden the spectrum becomes 1 over omega, which is good news and bad news at the same time, because of course if you now integrate over omega to get the total energy loss, you get a logarithmic divergence. So it used to be a very bad divergence, power-like. Now it becomes logarithmic, the divergence. Now with Gruzinov, we argued that the validity of our calculation was only up to some omega star of order, as indicated here, 1 over r times 2 extra powers of 1 over theta. So if you use that as a cutoff, as an effective cutoff, you find then a perfectly reasonable result for the spectrum. But, okay, so in that sense, the energy crisis is only partly solved because, well, we have to go beyond some approximations that we made, and we have to determine the actual value of omega star. We also have, in principle, to extend the calculation to arbitrary deflection angles and emission angles. Well, I put a question because perhaps I lost everybody at this point. Any questions?
You have 10 minutes remaining.
Okay, I'll try to accelerate then. So then the last subject is really the most recent one, which is black hole scattering. Now, we will be dealing with the hyperbolic problem, okay, the unbound problem. Now, there is a lot of work, in particular by Rafael Porto, about connecting the bound and the unbound problem, because, of course, from an experimental point of view, the most interesting problem is the bound problem, the coalescence. But, okay, we think, and Porto also thinks, that a lot can be learned from the scattering problem. So, well, perhaps I will go quickly, very quickly on this. in 2020, we sharpened and then solved a 3 p.m. puzzle. So as I said in my abstract, several puzzles are part of my talk. So this is just to remind people, there was an impressive calculation by Byrne et al. The full list is down there. That led to the first two-loop result in GR for two massive scalars. It was shown to be consistent and so on, but the interesting thing is that their result exhibited a logarithmic divergence as one goes to the massless or the high energy limit, in contrast with the finite result by ACV in 1990, which I showed in one of my first slides. There were a lot of discussions about that, and maybe I will skip the full argument and so on. So what we discovered in 2020 is that the Byrne et al. Calculation had neglected a whole set of contributions which would resolve this puzzle. This comes from integrating in the loops over a larger region of phase space. There is a so-called potential region, a so-called soft and radiation region, and somehow what happened is that in the Byrne et al. Calculation, one region was neglected. When you add both, then everything works out fine. This is the Byrne et al. Result for the phase shift to loop, which, as you can see, diverges logarithmically at large sigma. If you take sigma to infinity, sigma is like the Lorentz gamma factor. This goes to 1, but arc cosh of sigma goes like log sigma. So this is the logarithmic divergence. This was the puzzle. Now, when you add these extra contributions, you find two extra terms. Oh, this was done originally for n equal 8 supergravity because the calculation, believe it or not, is much simpler. Then I will show the extension or mention the extension to actual GR. But in n equal 8 supergravity is very simple. You get just these two extra contributions. Now, this contribution, as you can see, for sigma goes to infinity, also goes to 1. This factor cancels the 1. And so the logarithmic divergence gets subleading because it's down by a power of sigma. On the other hand, this other term also goes to 1, but has no log. And this gives precisely the old ACV 90 result. So the problem is solved by the additional, these two additional terms. Now, one has to observe that the old and new terms behaves quite differently in the non-relativistic limit. The non-relativistic limit is when sigma goes to 1 instead of going to infinity, and they correspond to even or versus odd powers of velocity, okay? The new and old calculation. So when we presented this result at a workshop in August 2020 on Zoom, Damour immediately grasped the meaning of what we had done. These half-integer Pn terms, these odd powers of V, meant that we had added to the conservative dynamics of Byrne et al. The effect of radiation reaction. And that fixed the problem. Now, in fact, a couple of months later, using a smart shortcut, Damour extended the result to GR. And so, you see, it's more complicated, the formula, but it has precisely exactly the same features as the one in n equal 8. The new terms cancel the bad behavior of the old terms. And now the only thing is to get the ACV 90 result, you have to add a few terms. You know, there are these funny numbers which add up precisely to this universal, because that limit is universal. So universality of the massless limit. And then we had our own derivation, shortcut. And okay, I will skip this. So the last subject I want to talk about is radiation and energy loss, because there seems to be a second energy crisis. When you go to order G cube, as I said, there is gravitational radiation, and a group, Hermann, Para-Martinez, Ruf, and Zhang, have computed at two loop the total energy radiated. And they found an interesting result, which actually agrees with Kovacs and Thorne, that the total emitted energy goes like theta cube times now a power of sigma. So you see that again, there is a problem if you keep theta fixed and you send sigma to infinity. Again, you find that there is too much energy emission. Now, but you have to remember the Kovacs, Thorne, and Diaz warning of the limit of validity of the result, which is theta s sigma to the 1/2 less than 1. So you see, if you use this bound, then in that situation, E rad over E is less than theta square, and there is no crisis whatsoever. So clearly the problem is somehow in taking the sigma goes to infinity limit at fixed theta, or take first theta to 0, and then, so it's like a non-commutativity of two limits. This is the full result of Para-Martinez and company, and you see this is the result. You know, it's rather complicated, but it simplifies a lot at high the ultra-relativistic regime, and you have this square root of sigma divergence. Now, an amusing fact is that already, if you already take the zero frequency limit and you integrate over a little range in which you believe the zero frequency limit to be a good approximation, which is up to omega equal 1 over b. You integrate the spectrum from zero frequency up to 1 over b, you already found a milder, but still a divergence of the same type. You see, you find that the radiated energy in this soft region goes like theta cube, which is okay, times a log of sigma. So strictly speaking, even just the soft region violates, you know, energy conservation if you keep theta fixed and you send sigma to infinity. But in this case, Mr. Weinberg tells us exactly how to cure the problem, because one can directly study the zero frequency limit for massless scattering. There is absolutely no problem, and the result is quite, has a subtle difference. It's finite, and instead of getting log sigma, you get log of theta scattering to the -2. So this is an exact result. In fact, I had it already in my previous transparency. It's also what we got with Krusinov and also by the other method. This is the famous zero frequency limit. Already the zero frequency limit has this non-analytic behavior in the Newton constant, because the scattering angle contains the Newton constant. So this is the price to pay not to have this divergence. Now, I see that time is running short, but so, okay, I will have to skip this part. Let me see what I should. Okay, so sorry, I had to skip a few slides because of time. In fact, you see, I already knew. In the rest of my time, if any, I will discuss what we did with the CFA. Yeah, okay, there is some interesting thing to do already for the soft radiation, which we carried out in this recent paper from last April. We studied carefully this soft region, and what I want to emphasize is the following, that if you study the soft region very carefully, you find that the zero frequency limit depends non-trivially on two scaling variables, which we call x sub I, which are the total momentum transfer of the collision divided by each mass, mi or m1 or m2, the two particles which scatter, the two black holes that scatter. Now, okay, one combination is just the ratio of m1 over m2, which is this famous nu parameter which is used. But the other is related precisely to the Lorentz boost factors. And it's precisely the quantity, the tricky quantity that Kovacs and Thorne have warned us about. Now, the dependence is non-analytic in G, and the Pn expansion in G has a finite radius of convergence. So this is what happens, that as you go to this regime, ultra-relativistic regime, you find that the expansion in Newton's constant has a finite radius of convergence. And one amusing thing, and probably that's where I will stop, is that you can understand this precisely from a particle physics approach, an amplitude approach. What happens is that there is a singularity at some unphysical point which corresponds to this xi square equal -1. Of course, xi is real, so this is an unphysical point which corresponds to a momentum square, q square equal -4 mi square, which of course is nothing but, sorry for the bad drawing, suppose I have this two-loop diagram. This blue and red line are our massive objects. They exchange soft gravitons. These are soft virtual gravitons, which are exchanged in the T channel. But there is also a soft real graviton, which is exchanged between this particle and this particle. Now, if you look at things from the point of view of the T channel, it's clear that there is a threshold if you go to positive T, which is negative q square, precisely at 2m1 all squared. So this T equal 4m1 square or m2 square are exactly the location of the singularities in the T channel, and therefore the presence of the singularity, by the usual mathematical argument, implies that the perturbation expansion has to diverge there. So that's another example of the use of some QFT idea. In particular, here is crossing symmetry. Now you can say, what the hell has crossing symmetry to do with black hole scattering? In the T channel, instead of having black hole collision, you have the annihilation of two black holes into two gravitons. You know, what kind of power? It seems like a completely irrelevant process. On the other hand, it is precisely this virtual process, you know, this unphysical process that provides this finite radius of convergence of the process. So it explains why this radiated energy fails. Now, this is only for the soft part of the spectrum. If you want to know the full spectrum, so I'll skip this, I will only flash this last slide. We have this is not yet published. It's to appear, I don't know when. But here we have a comparison between what we expect at different frequencies if you are below the KT bound or above the KT bound. And you see, I already explained this one. You go from a log sigma to a log theta to the -2. This seems to persist, this simple vocabulary, okay, going going ultra-relativistic. Again, here you replace a sigma by a theta to the -2. And now what we are studying, and we haven't finished yet, is the so-called hard region where you are above the sigma to the 1/2. If you want, you are above the knee of the spectrum, because in this case it's really going above theta sub s. And that's where we have a little problem, or I don't know, perhaps it's not a problem. Here we seem not to get, remember with Gruzinov and also with Ciafaloni-Colferai, we got 1 over omega behavior, which gave us this log. When we are below KT, we now checked, I have even graphs, I think, here, that the spectrum goes, there is a knee, in fact, at that point, but the spectrum falls faster than 1 over omega. This delta is of order 1, so it's more like 1 over omega square, the fall off, which then it gives a perfectly finite integral over omega. So if this is true also in this region, that means that we made some bad approximation in these papers, and the behavior is better than what we found, and then the log there. On the other hand, the cutoff that we guessed here seems to be completely confirmed. So, so I think we are on the way of solving or understanding the origin of this problem and even solving it. Okay, so these are my conclusions. So I want only to conclude that I think that this is a very interesting game from the point of view of connection with present experiments on gravitational waves. But I think, okay, just read the last sentence, that maybe this synergy between these two communities will also help us improve our methods of computing things, and we may eventually go back to trying to solve those fundamental questions in quantum, string gravity, like those that we asked some 35 years ago, and which we were a bit stuck with at the time. Okay, thank you very much.
Thank you, Gabriele. Do we have questions? No, don't be afraid. I won't throw it at you. Oh, come on. Yes, there we go.
Sorry, I'm sure I went too fast on too many things.
So I have a question about this eikonal operator that you mentioned. That
Oh, yeah.
my understanding is that is used to deal with infrared divergences. That you can you can include a matrix element for emitting soft radiation. Does it capture also collinear divergences? For example, because I was thinking that you mentioned that you're doing calculation also sometimes in
Sorry,
n equal 8 supergravity.
Which divergence?
Collinear.
Collinear.
Because you mentioned that also theories like n equal 8 supergravity. So
Yeah.
theories where you also matter around, where collinear singularities may be important. So is the eikonal operator like a generic a way to address infrared divergences, or is specific to soft?
Okay, so far we try to construct it for just gravitational interactions and where there are no collinear divergences, and it's only for dealing with the soft part. Now you are referring, say, to n equal 8 where there are gauge bosons and so on, and then there are indeed collinear divergences. My feeling is that it should work. Now, unfortunately, I finally decided to put on. This is not my computer, right? This is so I cut off the last part of my talk, which was already too long. But there, I had some additional slides where I was trying to put some other material. Also for possible discussions with some of you who are interested in more details, I have more material. But this may be relevant to your question because there we try to show that this eikonal operator also implements the Fadeev-Coolidge prescription for defining an S matrix between dressed states. Okay, you have this dressing of the initial and final states such that not only cross sections, suitably defined, inclusive cross sections are free from divergences, but even the amplitudes themselves between these dressed states. And so my feeling is that in that context, it should also work for collinear divergences, because I remember from the old QCD days that this is precisely the game we were playing to get rid of collinear divergences too. So my tentative answer is yes, it should work. It should work, but we haven't done it so far in this context. We only looked at so the idea, just since I didn't have time to mention it at all, is that all those divergences that I mentioned in the imaginary part, for instance, of delta, once you write things in terms of operators, they are sort of hidden, and they are no longer present, and they only come out as you take the matrix element between certain exclusive states, but otherwise, the operator is perfectly unitary and finite.
Other questions in the room?
Well done.
Sorry to stop. Thanks. So you didn't mention anything about this other line of research, which is asymptotic symmetries. So do you think there is something to learn from there, or it's just a separate topic?
Well, that's another subject which which is in the slides I did not copy here. I have them on my computer, but they are not in here. So there is a very interesting question about asymptotic symmetries, because the shortcut that Damour used to find, remember this finite result in GR for the deflection angle at 3 p.m., uses what is called a linear response formula, which was earlier proposed by Bini and Damour, which goes as follows. You say there is a radiation reaction due to the loss of angular momentum in the process. If you compute the loss of angular momentum, then using the Bini-Damour formula, that can give you the correction to the deflection angle or to the eikonal. Now, what was very So that's a puzzle inside the puzzle, if you want. That's how I was calling it. Is that in order for that to work, Damour needs that the angular momentum loss in gravitational radiation is of an order in Newton's constant, which appears to be too low. Namely, I think everybody who does, I don't know, Bremsstrahlung in QED knows very well this, if I scatter electrons and positrons and I want to compute the cross-section for emitting a photon, I have to go to some order in alpha, right, in the fine structure constant. Because first of all, I have to have my electron and positron scatter, which means already exchanging one photon, plus I have to emit a photon, so I need 3 powers of charge. And when I compute the cross-section, I get something about the alpha cube, right? Everybody would agree with that. Okay, in this case of gravitational scattering, the statement is that the gravitons would carry out some angular momentum at order g square. Although, you know, you need a power of g to scatter, and then a half power of g, a square root of g to emit. So how does it? It doesn't seem to work. So there was this puzzle inside the puzzle, and this is somehow related to the asymptotic symmetries, because you can show in the general theory of gravitational radiation by Bondi, Sachs, and Metzner, and so on, that the objects which carry energy and angular momentum at future null infinity are sensitive to BMS, you know, to these asymptotic symmetries. If you do a transformation which corresponds to one of these asymptotic symmetries, in fact a super translation, you can change, you cannot change the energy loss, but you can change the angular momentum loss. And you can change it enormously. You can make it from being of order g square to be only of order g cube. So you can get rid by super translation of an order g square emission of angular momentum in gravitational waves by a simple super translation. But if you get rid of this order g square angular momentum loss, you can no longer apply the Bini-Damour formula and get the result that you want. So I wrote a paper with Wilkowiski this year, and we pointed out that there is this BMS ambiguity, and we defined 2 Bondi frames, one which seems the one directly related to amplitude calculations, in which, unfortunately, you emit too little angular momentum to be able to use Bini-Damour. There is another Bondi gauge in which, indeed, you reproduce the result of Damour. And just this morning, just before coming here, I received a preprint or a draft of a paper by Massimo Porrati, which has a paper precisely on this subject. He elaborates further on my paper with Wilkowiski, and apparently he proposes a new BMS invariant definition of angular momentum loss, but I didn't have time. Otherwise, I would have missed the talk. So, but it's a very interesting subject, and really, I mean, somehow the community doesn't seem not to have reacted so much, but to me and to Grisha Wilkowiski, it sounded really very difficult. So this is somewhat associated with the emission of exactly zero frequency gravitons. But what is an exactly zero energy graviton? Well, it looks more like a static field than a radiation field. So it's a very interesting topic of the interplay between radiation and static field, and how you can lose angular momentum not only to radiation but also to the field itself, which sits, you know, at some finite distance from the process, not radiated at infinity. So it's a very interesting topic.
We have perhaps a last question that was asked on Zoom by Rafael Porto. So what about the log gamma divergence of the full result recently computed at g to the fourth?
Yeah. Yes. In fact, I have corresponded a little bit with Raphael. As I mentioned, at 3 p.m. there is this gamma or sigma to the 1/2 divergence. Now, what Porto and his collaborators have worked out, and they are already, their paper has been out very recently, and there is also one by Thibaut Damour on 4 p.m. At the same time. They found that this time there is a log delta, a log gamma or log sigma divergence in the deflection angle. So, in the emitted energy, but if I remember well, also on the deflection angle. And, well,
So in the angle. He confirms.
the angle.
Also in the angle.
Also in the angle. Also in the angle. Now, yeah, my feeling is that it could be that the 3 p.m. story that I described, where everything goes smoothly and so on, may be a lucky situation at 3 p.m., which may not repeat itself at higher orders. This is my feeling. Now, in corresponding with Raphael, I mentioned to him that perhaps we have some understanding, but at the level of the energy emission, why things are a little bit better at 4 p.m. than at 3 p.m. Because when you put everything in their result, express everything in terms of deflection angle and Lorentz boost, at 3 p.m. you get theta cube square root of gamma. At 4 p.m. you get theta to the 4th log of gamma. And we have some understanding of why 4 p.m. is a little bit, is less severe. And this has to do with the fact that in the massless limit, the even PM seem to be depressed or completely absent. As I mentioned, if you remember, at 2 p.m. we had this 0 classical result. At 3 p.m., non-zero. Now we expect that at 4 p.m. the massless limit is again trivial. The true massless limit is again trivial. And so this has to be still understood, but it's a very recent result, and we are thinking about it. I don't have a definite answer.
So it's getting late, so I think that we can thank Gabriele again. Two pieces of information. Gabriele, you're staying in the afternoon, I suppose.
Yes.
He's in the office 116, if you want to come and chat.
I am available whenever you want. Yeah.
And something else is that we have another talk today by Paolo Creminelli at 4, yes, I think, in Itzigson. Okay. Thank you for coming again, and have an excellent afternoon.